All right, well, I think we've got a great audience pulled together. Thank you everyone for joining us once again. Thank you for joining this joint session of the Boston Society of Architects Committee on the Environment and the SCUP College and University Roundtable. We have a great panel for you tonight. Before I introduce them and the topic, I want to let one of the co-chairs of the SCUP College and University Roundtable, Debbie McDonald, say a few words. Debbie, you're on mute.
There we go.
Yep.
Sorry about that. Been diligently on mute. I'm Debbie McDonald, higher ed market sector leader with Jacobs and co-chair of the BSA SCUP College and University Roundtable, together with Donna Donaio, founding co-chair of the committee, who is with us today, and Niyusha Arndt, designer with Perkins & Will. Last spring, we focused on reacting to COVID and what measures campuses were taking to get through this pandemic. This spring, we are focusing on planning for 2022 and beyond. We are collaborating for this session with the COTE committee on decarbonizing campus. Patrick Murphy, who is Associate Principal and Director of Sustainable Design with Vanderweil, is a BSA SCUP committee member, also co-chair of the COTE committee and organizer and moderator for this session. Patrick.
Thank you, Debbie. So on behalf of the COTE committee and my co-chair, Michael Grant from Stantec, a couple of announcements for those of you in attendance. We are actually coming up to the end of our terms as co-chairs in June, and at the June meeting, this again, same third Wednesday of the month, we will have elections for new co-chairs. And anyone who is interested in participating in the BSA COTE committee as a co-chair is certainly welcome to reach out to me directly. You can just chat me here in the chat window or follow up with me afterwards. And we'll actually have a call for all interested parties that want to explore being a co-chair next week, and we'll answer questions about what it's like, what the responsibilities are. And again, we'll have that election in June. So anyone who is interested in weighing in on, even if you don't want to be a co-chair, but want to vote on the co-chair, we ask that you attend next June. So with that, let me introduce our distinguished panel and this great topic, one that's near and dear to my heart. So, my interactions with higher ed clients are inspiring because they're leading the way as an industry around buildings towards decarbonizing, towards sustainability in general. And we're seeing this massive shift in the way that we think about and use energy on campus and the way that that impacts emissions. Each college has their own unique set of circumstances that they are designing around. And today we have three different colleges represented to share what their experiences are, both on the years of addressing individual building energy conservation measures, but also planning for the future and strategic strategies for long-term emissions reductions towards the net zero energy and net zero carbon commitments that many colleges and universities have made. So with that, I'll introduce our panel. We have two representatives from Amherst College. The first is Jim Brassard, Chief of Campus Operations, and Mark Tassinari, who's a Senior Project Manager at Amherst College. The next presenter after that will be Abby Bjorklund, the Director of Engineering and Utilities at Dartmouth College. And finally, we'll have Mina Amundsen, an Assistant Vice President for Facilities and Campus Planning from Colby College. I've had the pleasure of working with this group either professionally or in the development of this series. Even just the interactions between them were really rewarding and enriching. And I'm sure you're going to have a great, you're going to learn a lot and have a great session tonight. So with that, let me hand it off to Mark to begin the presentations.
Okay.
Hello, everyone. Hopefully you can see my shared screen at this point. It's good to be with you all, sharing this information. And to start the presentation, Jim Brassard is going to take us through the first slides. Jim?
Thanks, Mark. So pleased to be here tonight to talk about our experience with decarbonizing our campus. Our trustees in 2016, based upon the moral imperative of climate change, set an aspirational goal to achieve carbon neutrality. And at that point did not set a specific time, but committed us to doing the rigorous study necessary to chart a path forward. And emphasize that the goal was at that point carbon neutrality, but that has really evolved into true decarbonization of our campus. And that's an important differentiation that I will get into as I walk you through our plan. But I think first, just to provide context and background a little bit about our campus. For those of you who don't know, Amherst College, small private liberal arts campus and college in Western Massachusetts. We have about 82 buildings defined by a core campus served by a central utility infrastructure and peripheral buildings that blend into the surrounding town. Our campus is about 2.2 million GSF with some anticipated growth in future years, but only modestly so. Next slide. A little bit about the legacy infrastructure that serves the campus currently. And as we researched our forward-leaning strategies, we had to draw a through line to the past. And interestingly, we found that in 1924, our trustees, faced with the crisis of pollution on our campus from particulates from burning coal and wood, with resiliency challenges as a result of numerous fires that had occurred in the fireplaces and individual boilers and stoves on our campus, made the bold move to say they had to transform our infrastructure. And with the technologies emerging in that day, they made a massive commitment to build a central utilities plant and steam distribution throughout the campus. Interestingly, if we normalize the cost for that initiative in 1924 to today, based upon escalating the cost and expanding the campus, it translates to about $50 million, which I thought was striking and showed how bold they were in 1924, and that we are upon that next bold move with the existential crisis we face with climate change. So our heating systems, we have a conventional fire tube boiler system that distributes steam through the campus. And recently, in the relative recent past, 2007, we introduced a combined heat and power plant that generates about half of our electricity and about a third of our thermal on campus. We have central chiller plants, and all told combines to greenhouse gas, both scope 1 and scope 2, of now about 17,000 metric tons per year. But that does represent a substantial decrease from what we saw in prior to 2006. So we go to the next. Now, the interesting thing, as the trustees put forth this challenge, convened as we do on colleges, committees, of course, and broadly representative. And the initial approach for that committee was to try to achieve carbon neutrality. And we looked at a number of different things. And primarily it was around how can we conserve our way towards that? And how can we gain efficiencies? And so we soon realized, though, that doing less bad was never going to get us to the point where we could be not just carbon neutral, but decarbonized. And the recognition is that carbon neutrality, if achieved through offsets that had kind of specious origins, was not truly in the spirit of what we needed to do to be leaders in this realm. So we developed a set of principles, and they're pretty self-evident, but just to touch on them, minimizing the on-site created emissions through combustion, maximizing use of renewables, minimizing reliance to the extent possible of carbon offsets. And we wanted to be a leader. We wanted to be able to be forward-looking and be an exemplar, not only for peer institutions, but an exemplar for our students, so that they could take lessons learned from the initiatives on campus forward to their post-Amherst lives. And it was also a great intersection for us because this legacy system that I referred to is aging. And you know, although the components of it have mostly been renewed over 100 years, it is a 100-year-old technology that within the next 10 to 15 years will require a major infusion of capital. Go to the
if
next.
I could interject, Mark, just to help everyone be able to see the screen a little bit more clearly, could you go into the presentation mode to enlarge the screen? There's on the bottom right next to the Zoom, just to the left of that, there's a button that looks like a screen on the bottom right.
Go to the very bottom, Mark.
Where?
Bottom of the slide. Yeah.
And now to the right.
Keep going.
Two more. The one that looks like a screen. Yep, that's the one. Perfect. Thank you.
Okay. So what does decarbonization look like for Amherst College? And what did this committee come to in terms of an approach? First thing is that we brought aboard an energy consulting firm, the Integral Group, that has deep experience in this through an international practice, and brought many of the approaches and sensibilities that have been adopted in Europe and really represent cutting edge to us, and helped us to understand the issue of conservation and efficiency was not sufficient to get us where we needed to be. And so this is essentially a very simplified schematic of the elements of our system and what we have now proposed and are now moving from concept to design. So first and foremost is that we needed to drive down our energy use intensity across the campus and to maximize energy efficiency. So we are involved in a program, an aggressive program, to be able to enhance efficiency and reduce the thermal load of our buildings. Second is a conversion to low temperature hot water as a medium for heat transfer in lieu of steam. Steam is just inherently inefficient with the conversion losses, and then the delta T, the thermal conduction that one sees through the distribution heat loss. The next element of the plan is to electrify both our heating and cooling through phased implementation of ground source heat pumps and supplemented by air source heat pumps for details that we'll get into a bit later. And then to combine the central cooling systems, which are now in districts and on individual buildings levels, and combine them into a system that would allow for simultaneously heating and cooling, concurrent operating modes with buildings through the heat pumps. And then the final things are really is that we wanted to be able to address the electrical requirements for this electrified infrastructure through renewable sources, whether they be through offsite power purchase agreements or through on-site generation. So acknowledge that there may be some requirement for residual carbon offsets for any of the minimal greenhouse gas emissions that would result from resiliency measures for backups that may require some burning of fossil fuel. So really the key concept to this and to achieving this decarbonization is introduction of the ground source heat pumps, a major heat pump plant. Now the concept here really is that a heat pump is a means to transfer energy and transfer it from one source to another and to add or take heat from that. In essence, a heat pump, which you're probably all familiar with at a residential scale, can run in either direction and can use, in this case, because we're either obtaining or rejecting heat from the infinite heat sink of the Earth, it can use the Geo resource as a massive battery, a battery that either we in the winter use as a heat source, extract that heat, raise its temperature, and then transfer it through a distribution system to the buildings. Or in the summer, run in the opposite direction and use the buildings as the heat source and transfer that heat back to the massive Earth battery as a heat sink. Now, the key to this really lies in the fact that it has a coefficient of performance that far exceeds what you would see from conventional boilers or from chillers. They typically have coefficient of performances of less than 1. And what we see with a ground source heat pump is that it's typically in excess of 3, either in the cooling or in the heating mode. You can really gain true efficiencies is when you use the heat pumps for simultaneously heating and cooling. And that is to say, at various points of the year, in fact, for Amherst College, every point of the year, there are times when we have buildings that are in the heating mode, and there are times where we have buildings that are in the cooling mode. This is a plot of what that thermal profile looks like for Amherst College. And you can see that across the seasons, in the depth of winter, there's very little cooling that's required and a significant amount of heating. But at that same point, you can be able to use the simultaneous heating and cooling to boost the efficiencies of the heat pumps. When we get into the shoulder seasons and into the summer months, we see that there's much more overlap. And at this point, we're able to run the power plant, the heat pump plant, at a coefficient of performance of 6, fully 600% more efficient than we have with our current systems. So as I noted earlier, really critical that in order to power this system, we source renewable electricity. We are currently establishing a PPA with a consortium for a utility scale PV array in Farmington, Maine, that will power and provide roughly 50% of our current power demand. And I think this sets the stage for us to say that as the electrical demands for our systems increase in future years, that we could enter into additional PPAs to supplement that. And we're also considering on-site renewables. We have over 1,000 acres of land adjacent to the college that would be nicely situated for such an initiative. And of course, desire to minimize carbon offsets, and we just don't feel that that is necessarily in the spirit of what we're trying to do to truly decarbonize our campus, and that there is always some level of doubt as to whether offsets create the type of additionality for renewable power that we really seek. This is just another articulation of the simplified schematic that I showed before, and it allows you to see the major components that are now in the design process for our decarbonized infrastructure. The central energy plant with the heat pumps, supplemented by air source heat pumps that will run very efficiently and effectively during the course of shoulder seasons when we don't necessarily need the full volume and capacity of the earth bank. Solar energy to power it, the interface with the geothermal wells, which is noted at the bottom of the page, and then distribution of chilled water and low temperature hot water to the buildings. And within our existing boiler plant, retaining hot water heaters and chillers just as a resilience measure in order to address any sort of compromise to the new energy center. A key concept that we quickly learned in working with the Integral Group is that selecting the operating temperature for the new low temperature hot water loop is really critical. If the temperature is selected at too low of a level, what it does is it creates the need for massive investments in the buildings so that they can operate at that low temperature. And the other issue, though, is that if you try to create too high of a temperature with the heat pumps to offset that capital investment in the buildings, well, you run into a lot of difficulty in sourcing those type of heat pumps that can lift heat to that level. So there's a sweet spot. And for us, that sweet spot that we've developed and tested empirically is about 130 degrees. Anything less than that, and our buildings will not heat properly. Anything more than that, we're getting into the realm of very, very expensive heat pumps and difficulty in sourcing those. So I think this is a good point where I'll pause, and I'm going to turn it over to Mark, and he can talk about the specific details of our plan that may be of interest.
Thanks, Jim. Hello, everyone again. So, of course, this new heat pump plant that we're anticipating is reliant on the ground source heat exchangers, also known as wells or bores that are set into the earth. The installation and performance of these exchangers obviously is dependent on the geology that's present at the site. So in order to determine what we're dealing with specifically on our campus, we installed this last spring, a test bore, which included an 800-foot deep bore and continuous U-bend heat exchanger. What we found was all good news through that test bore. First, there were good drilling conditions. Minimal groundwater protection, which is an important aspect of controlling water as you're drilling. And most importantly, we found good to excellent thermal conductivity in the soil, which of course is the soil's ability to transfer heat effectively. So our engineers are using that information now as they embark on the design of the first phase of the well fields. So the location for those geo exchangers we expect to be in our athletic fields. As you can see from the diagram, we have about 10 acres of field available between our soccer fields and baseball diamond. We expect to need about 4 to 5 acres. We're anticipating maybe 400 to 450 bores across that area. Key point to make about the geo exchange field is that it will be developed in phases. And that gives us a couple of advantages. First, it allows us to at least mitigate the impact to athletics by taking off just one or maybe at the most 2 fields at a time. And also importantly, it gives us the opportunity to gather empirical data to see how the initial field is performing in the first phase. And that data can be used then to inform subsequent phases and really dial in and right size the subsequent phases of the field. So the Energy Center is going to be a significant building housing the new heat pump plant. We struggled with various locations. We looked at a few locations close into campus. We found that those were not desirable from a campus planning perspective. First of all, we're anticipating some rooftop equipment that's going to be, among other things, loud. Probably not ideal for close proximity to academic and residential buildings. So we settled on a site, or a rough site at the perimeter of campus, which besides dealing with the noise factor, also preserves these more high-value sites for future academic buildings or possibly residential buildings. Obviously, resiliency and backup is critical, especially as we're looking to the future with the increased likelihood of extended power outages from extreme weather events. Our plan anticipates that and includes full resiliency, provided in a couple of ways. First of all, the heat pump plant itself is so electricity intensive that it's just not feasible to generate that much capacity on campus. So for the heating component, we will be using new high efficiency natural gas or biofuel boilers that will be there not only for backup events, but also to supplement the heat to the heat pump system during extremely cold snaps during the winter. We'll also be expanding our emergency generator capacity to make sure that the system is running. That's more circulation pumps, not running the actual heat pump plant itself. And then combining that additional capacity with our existing capacity gives us the ability to essentially run the campus in a business as usual way during extended outages. So the phasing, the project is comprised of 4 to 5 phases, depending on how we count them. Phase 1A, seen here, is really the establishment of the first leg of the low temperature hot water network on the east side of campus. This will leverage some of the newer buildings that we've designed that are largely designed already to accommodate the low temperature hot water. In addition, we'll be making some modifications to a couple of our older buildings to make them low temperature hot water compatible. You'll notice that in this phase, we haven't started construction of our new energy plant or the Geo Exchange field, but we will be installing new steam to low temperature hot water heat exchangers in our existing plant, and that'll feed the low temperature loop, this first leg of the low temperature loop, and allow us to take advantage of those efficiencies versus the steam system. Phase 1B is the largest single phase of the project. It extends the loop, the new distribution loop, to the west, basically creating a loop around the core of the campus, brings on about 16 additional buildings. It's when we construct our new energy center here down in the lower right corner of your screen, and the first phase of the Geo Exchange field. So when this phase 1B is completed in 2025 timeframe, roughly, we'll have more than 50% of the campus on the new system. Phase 2 expands.
Mark, sorry to interrupt you, but just so that we can also get to Abby and Mina, can you skip to the overview of all of the phases and just speak to that and then the alternates?
Sure. Yeah, we're running a little behind time, so I apologize for that. So at the fully expanded build out of the project, you can see it colorfully shown here. We're running all the campus, including our peripheral buildings, off of the new Geo Exchange fields in our new Geo plant. When priced out, that gave us a total escalated cost down here in the lower right corner of about $113 million. So we went to work at the obvious next phase, which was the value engineering phase, identified a couple of alternates. First was to look at deferring the work on our peripheral buildings, which, although they represent about 13% of our gross square footage, only represent about 5% of our greenhouse gas emissions. So not a lot of bang for the buck in terms of reducing our carbon footprint. The other option we looked at was to segment the hot water loop into a high temperature zone and a low temperature zone. This allows us to defer some of the capital cost of the building conversions that are necessary for the low temperature water to a future time when those buildings would be normally up for renovation through programmatic changes or just end of useful life. Both those options look pretty good to us, so we created a third option, which we basically combined the first two. Both the core campus and the Carleton model. I should have mentioned that Carleton College has done something similar to the split loop with a high temperature and a low temperature zone effectively. So we adopted that. When those two options or alternates are combined, we realized the cost of about $82 million, which is roughly $30 million savings over what we called our base option at the start. So at this point, I'll turn it back to Jim to talk about some of the financial aspects of the project and its impact on our greenhouse gas emissions. Jim, you're on mute.
Thank you, Mark. So I realize we're short on time. I'll be brief on this to say that the financial aspect of the project was really critical, and we like to think this is where environmental sustainability meets financial sustainability. And I think from this graphic, the high-level takeaway is the business as usual and continuing with our legacy system would have resulted in an MPV over a period between now and 2050 of about 225 million versus the other options. And you can see alternative 3, which is the one we finally selected, of 206 million. Of course, much more capital intensive, but the true savings that we achieve really is in terms of the operations and maintenance and the energy component of it. We see that there is a break-even point for this, and even factoring in potential debt issuance, we are out about 15 years after final implementation for a break-even point. Built into this model is a cost avoidance of carbon taxes that we anticipate will be levied, and some of the fees that Massachusetts is considering. And here what we show is a wedge chart in terms of what our savings are. The image on the left, if you look at the horizontal line at the top, that's business as usual with our 17,000 tons. But you can see on the basis of essentially implementing energy conservation measures, the conversion to the low temperature hot water with the Geo exchange, and then replacing the grid purchase electricity with renewables, we get down to a very low carbon emission and one that we feel comfortable that with quality offsets, we can feel that our plan is solid and is an exemplar for our students and beyond. So with that, I'll pause and I think turn it over to Patrick.
Thank you. Next up, we have Abby Birkeland from Dartmouth to share. We can see your screen. Great, thanks. And you're on mute, Abby.
Okay, can you hear me? All right, good. So I'm going to give you a quick overview of where Dartmouth College is on our sustainable energy journey. Are you guys, oh, there we go. So Dartmouth is the smallest of the Ivy League colleges. We're located in Hanover, New Hampshire, in the woods, basically far from any major cities. We're about 5 million square feet, 130 buildings. We, similar to Amherst, have an old, over 100-year-old central steam plant, which is providing heat to our campus. We're distributing 20 PSI steam to the buildings, most of the buildings on campus. We also have about an 8,000 ton of chiller capacity. Most of that's located in our north and our south chilled water plants, though we do have several other chillers scattered around campus that are serving just 1 or 2 buildings. We spend about $12 million a year on energy, and about half of that is used to burn number 6 fuel oil in our central plant. Unlike Amherst, we are not near any gas pipelines. We're about 60 miles away from the nearest pipeline. So we are dependent on liquid fuels for our plant. So in 2016, the campus president appointed a sustainability advisory board of faculty and students and staff that developed sustainability goals that were adopted by the campus in 2017. And our energy goals include reducing our scope 1 and 2 greenhouse gas emissions by 50% by 2025 and 80% by 2050. Also upgrading our aging infrastructure, improving the efficiency of our distribution systems, and converting to 50% renewable energy by 2025 and 100% renewable by 2050 with a 2010 baseline. About the same time in 2017, the town of Hanover, New Hampshire, where we're located, adopted renewable energy goals for the town, and Hanover was the first town in New Hampshire to set the goal to be 100% renewable. So electric by 2030 and heating and transportation by 2050. So this is where we are in terms of our campus scope 1 and 2 greenhouse gas emissions. As you can see, we've been working on energy efficiency improvements over the last 15 years or so. We've steadily dropped our carbon emissions while at the same time increasing our campus footprint. But you can see that we're only about halfway to our goal for emissions reduction by 2025. And this pie chart is showing what are the sources of those emissions. So the biggest portion of that, the dark brown, is the number 6 fuel oil that we're burning at our central steam plant. And the other big lighter brown portion of the pie is the grid electricity that we purchase. The rest are smaller emissions from number 2 oil and propane and other fuels that we're using on campus. So you can see from this pie chart that our biggest opportunity is to reduce the emissions associated with our central heating plant. And like Amherst, steam systems are pretty inefficient. We're estimating that only about 60% of the available energy in the number 6 fuel oil that we burn at the plant is actually resulting in usable heat in our buildings due to the losses inherent in a steam system. Our steam distribution system is also aging. This is our campus map with a condition assessment, and the steam lines that are purple and red and yellow are our oldest lines. They're all over 50 years or more in age, and we're anticipating that to renew those aging systems would cost us $61 million over the next 30 years. So in 2016, we initiated a study for our campus looking at how could we renew our aging infrastructure and improve the resiliency, energy efficiency, and reduce the greenhouse gases on our campus. So one of the major recommendations that came out of that study was to convert from steam to hot water distribution, which is much less expensive to construct and to maintain. It also has much lower heat losses. And a big advantage with hot water is that it can easily integrate different energy sources like solar thermal or heat pumps or geothermal or fuel cells. So we developed this vision based on the 2016 study of where we want to bring our campus. And it all fundamentally rests on improving the energy efficiency of our existing facilities and designing our new facilities and major renovations to our existing buildings to be high performance buildings. And in 2016, we adopted our high performance building energy policy, which you can see on our website, which requires that for any major capital project that we do energy modeling and life cycle cost analysis and look at design alternatives and fund them if they have a positive net present value over the life cycle. So we did that, for example, recently on our Dartmouth Hall renovation project, where the campus decided, even though it would add significantly to the construction cost, to add insulation to Dartmouth Hall as part of that renovation because it had a positive savings to investment ratio, which could be justified over the lifetime of the insulation, and it would reduce the energy utilization index of the building by over 20%. So a key part of this vision is developing our district hot water system to heat the campus. And the biggest part of that is converting the buildings from utilizing steam to utilizing hot water. And for our campus, I think similar to Amherst, we have a lot of 100-year-old buildings that have their original steam radiation systems. And there's going to be a lot of work to convert all of those systems from steam to hot water. Another key part of our 2016 plan is to build a new biomass heating plant to replace our existing heating plant. So the new plant would utilize locally sourced renewable wood chips as the primary fuel source. Another key part of the 2016 study was to interconnect our chilled water plants and our buildings on campus and to install heat pumps, as Jim was talking about at Amherst, to utilize the waste heat from the condenser side of the heat pumps to provide heat to our heating network and cooling to our chilled water network, and be able to exchange heat between buildings through those networks. And also to integrate thermal storage, chilled water and hot water thermal storage. Also to expand renewables, both PV and solar thermal on our campus. So when you pull all of those pieces together, we have a vision of a future campus with an energy system that is renewable and flexible and positions us well for the next 100 years. So in 2019, Dartmouth issued a RFQ to developers to develop a new biomass heating plant for the campus, and also to develop our district hot water system and to execute our building conversions. And also at that time in 2019, we had a major effort to develop schematic designs for all of our building conversions. And we did all of that work for 129 buildings in less than a year. And we brought on about 6 or 7 different consulting firms to help us get all that work done. And it was a major effort. And it included not only the hot water conversions, but also it included code updates. For example, a number of our buildings don't meet current ventilation codes. So we added heat recovery units in those buildings. And we all know now with the COVID-19 experience how important ventilation is to our building designs. We also incorporated a lot of capital renewal where needed, replacing HVAC equipment, controls, electrical upgrades, emergency generator upgrades to provide backup power to our new hot water systems. And we included energy efficiency improvements where they were cost effective in those designs. Another key part of those schematic designs was adding central air conditioning to 42 buildings on campus that currently don't have central air conditioning, which includes most of our housing facilities and several of our older academic buildings as well. And another part of the schematic design was the design of our campus hot water network, as well as the additional chilled water network to provide chilled water to buildings that don't have central cooling now, and then upgrades to our central chiller plants to provide the added capacity that we need for those 42 additional buildings, plus replacing aging chillers with new efficient chillers and heat pumps. Another part of that schematic design effort was developing a multi-year phased implementation plan for how we are going to convert the buildings based on the construction time needed to execute those schematic designs and the available swing space we have for the buildings that we have to move people out in order to do that work. So this map gives you a picture of where we are now with our campus heating systems. Each of those circles represents a building's heating load. The big circles are big loads, the little circles are smaller loads. And the red are our existing steam systems. The green are existing hot water systems that we have on campus. So as you can see, we've got a lot of red there and a lot of work to do. And this map shows our existing buildings with central chilled water from our north and south chilled water plants. So this is where we are now in 2021. We've completed the build out of our first campus hot water distribution system. And you can see my cursor here, which starts here at the north end of the campus. We have a steam to hot water conversion plant, and then we're distributing hot water over to the west campus. We have two buildings that are completing construction this year, our Irving Institute of Energy and Society and the new Thayer Computer Science building, which are the two green buildings on the west campus. So those will be taking chilled water and hot water from our new distribution system starting this summer. And we're also in the process of designing hot water and chilled water conversions to several other buildings. Here you can see the new chilled water distribution going to provide chilled water to Dartmouth Hall and Thornton and Reed, which are buildings that are recently under construction for major renovations and incorporate hot water conversion and additional air conditioning. And I'm just going to quickly scroll through our implementation plan. As the buildings turn blue, that means that they are converted to hot water and connected to our campus distribution network. So right now our plan is to have the campus hot water conversion completed by 2034. So this is where we plan to be in 2034 based on our current schematic designs. All the buildings are converted to green. And this is our new chilled water campus network with cooling, central cooling provided to the 42 additional buildings on campus. So we're predicting that the result of this effort between the efficiency improvements from the steam to hot water conversion and the efficiency improvements in the building designs will result in a 31% greenhouse gas reduction for heating and cooling energy in our existing buildings. And that does take into account the added energy associated with air conditioning. But the benefits of this are not just the greenhouse gas reduction. it's also going to be a major renewal to our aging building systems that are in need of capital renewal. Not only our heating systems, but also our control systems, our HVAC systems. We're going to be adding central air conditioning to 42 buildings and removing hazardous materials, renewing our emergency generator systems. Overall, we're estimating our campus facility condition index is going to improve by at least 15% from this initiative. And we'll be able to incorporate a range of non-combustion technologies to generate the hot water from heat pumps and geo exchange or other systems. So in late 2019, we started to rethink the decision to build a new biomass heating plant and started to rethink whether combustion technology, even if we're utilizing sustainable, locally sourced resources, is really a good investment for greenhouse gas reduction. So we conducted a high-level study, which was completed in early 2020, of alternatives to building the biomass plant. And the result of that study was a recommendation that we build out 3 regional geothermal fields and heat pump plants on our campus, similar concept to Amherst. And that would provide 63% of our heating requirements for the campus. To build out a solar thermal plant, which would provide 7%, and to replace the steam boilers in our heating plant on in a phased manner with new hot water condensing boilers that would utilize with liquid fuels, either biodiesel or No. 2 oil. And to bring all of our campus hot water systems to low temperature operation. Our original schematic design was converting all of our steam systems to low temperature, but not all of our existing hot water temperatures. But as Jim was saying, if you lower your hot water temperature, you'll have a lot more heat pump technologies to choose from, and your heat pumps will be more efficient and your condensing boilers will be a lot more efficient. So this is a schematic or a map of the plant showing the schematic layout. You can see it includes a geothermal field and heat pumps on the north end of campus, another one on the west end of campus, and another one in the south part of the campus where we'd be installing geothermal wells on our green, where we actually did do a test well a couple years ago. So based on the results of this study at the end of this past year, the campus announced that we were not going to build our biomass heating plant, that we are planning to continue with our campus hot water conversion, and that we will be developing low combustion energy sources to provide heating and cooling on our campus. So all of this work was pretty much on hold for the past year due to COVID-19, but we've been recently starting it up again. We have authorization from our board of directors to conduct a more detailed follow-up study to the high-level study that I was just talking about for the low carbon energy supply sources for our campus. And we're also working out our implementation and funding plan for all of our building conversion work as well as the plant work over the next 10 to 13 years. Most of that work is the building conversion work. And as I mentioned, we're already in process there. We have our West Campus Hot Water District that will be starting up this coming summer. we're now starting designs for interconnecting several more new and existing buildings to that distribution system, and expanding our chill water distribution. We have major renovations that are starting design now for some of our housing facilities, as well as the Hopkins Center, which is our major arts facility, where we are converting to low temperature hot water and adding air conditioning to those facilities. And we're also starting on some additional deep energy retrofit projects. We executed one a couple of years ago in one of our major lab buildings, and were successful in reducing our greenhouse gases by 80%. So we're excited about more of those projects being implemented in conjunction with our campus hot water conversion. So that's the summary of where we are, and I will hand the floor over to Mina.
Great, thank you, Debbie. And Mina, let's bring us home. And I think those of you in the audience, you might start to already know you're seeing some parallels between these colleges, which we'll get to in the questions. And a reminder, anyone who has questions, put it in the chat and we'll get to the questions after Mina's presentation. All right, go ahead, Mina.
Thank you, Patrick. And I just wanted to say hello to all the many familiar faces on this call. Thank you. It's delightful to see everyone. So I'm so happy that I've kept my presentation short, because I've really enjoyed hearing both, Jim, Mark, and Abby, and we have a lot in common in many of the things that we're doing. So what I'm going to focus on is actually what you do beyond once you are carbon neutral, and what you have to do after that. And, the approach that Colby is taking.
Mina, as you get going, there might be something rubbing against a microphone. We're getting some feedback.
Okay, is this better?
It is.
Okay, I'll try to breathe slowly. So just a little bit about Colby. I'm not going to repeat read up what's on the screen, but the institution is, a little over 200 years old, and the Mayflower Hill campus, it's another interesting story that I will tell about another day. But the campus was actually built, the core was built almost in a piece in the 50s, so right after the war. And so we're at an interesting point in terms of both looking ahead at some pretty robust expansion, but also pretty significant renewal that's happening all at once. And the other piece that I wanted to share is that the college has been carbon neutral since 2013. And Colby was the fourth in the US to be neutral. And I think the other three institutions have, I think 2 have closed down and 1 has not maintained neutrality. And I think what we are going to walk through a little bit is getting there, staying there, and then, how do you maintain it in a way that still continues to push the boundary? And as Jim mentioned, it's not just enough to look at energy, you have to really comprehensively decarbonize. So, since 1999, we've been making changes that are both, in our energy systems, but also governance. So our environmental advisory group, the EAG, was formed in 2000. So that's the group with senior administrators. It's still headed up by our VP for admin and our CFO. So it has some pretty high profile support, and it has students and faculty. We have a rotating group. So and Patrick, that is not me. So again, what we've been doing is successive actions. And I think many of you have also been there. And, we became carbon neutral in 2013. And when I came on board in 2015, we were in the process of actually developing a solar array, like a major one that would give us, and as it states, 16% of our campus demand, which again, it still continues to grow. We adopted our sustainability action plan, and then, now and moving ahead, we keep pushing, so people believe in LEED or not believe in LEED. It's not so much a matter of us thinking LEED is the way to go, but it's a way to measure and to quantify and to express, I think, what we're doing in our goals. So we keep raising those standards as well. So when we got to neutral, the approach was really to get to 100% renewable electricity. So we were already there in 2002. Using biomass as a primary fuel source. We are in Maine and logging is a big industry and there's a lot of waste wood. So that's what we use in our plant. And then, like everyone else is purchasing carbon offsets for the balance that you cannot cover. So the trajectory from 2000 to 2020, as you can see, the dashed red line is if we just did nothing and kept burning number 6 oil. So, it sort of really puts the key highlights and milestones. And then, in the bottom right, we have the offset purchases. And one of the things that we're trying to do is not buy the cheapest offsets. We actually spend a fair amount of money on them. And we are actually following the UN's guidelines. They have a whole detailed series of what you have to consider. And so we measure our offset purchases against environmental, community, and economic benefits. So, so then getting to our greenhouse gas emissions, I did want to kind of use the story of, the 20-year story to talk about kind of the journey and how, we, what we're doing kind of pre and post neutrality. So if you can see we built the biomass plant in 2011, and you can see a significant drop, in, the use of heating fuels. But I do want to point out the reason we're taking a holistic approach is at this point in 2020, you have almost an equal amount of emissions from our heating fuels as we have from our travel. Stubborn darned thing that won't move. So we do have work to do. And so continuing on, I didn't want to sort of repeat a lot of stuff. So moving on to our consumption and looking forward, the thin blue line that's at the top is our campus gross square feet. So 2013, we were somewhere upwards of 1.4 million. We are continuing to climb. And we got a new president in 2014. There's been a very ambitious program of expanding. It's academic programming, but then that represents itself in buildings. And so at this point, we're a little over 1.6 million. And by 2030, we expect to be 50% over what we were in 2020. So that's a pretty significant growth. And so that comes with an increase in demand for energy. And so we're trying to be proactive and get there, and have a plan and also systems in place so that we don't have a huge spike in, these bars. So one of the things that we're also seeing with the use of our wood chips is maintaining those darn boilers. It's very different from number 6 oil, and we've been increasing our reliance on natural gas. And if you look at the big picture, Maine is at the end of the line as far as natural gas goes. So if you're in Pennsylvania, it's one thing, New York, it's one thing. Up in Maine, we're quite literally the end of the line. So one of the things that we've been sort of thinking about ahead of time is, do we really want to depend more and more on natural gas? It is a fossil fuel. So we'd like to really move away from that. So how do we get there? So, we're doing fine so far, but, we need additional savings in energy use because we have to offset a pretty large new building we built, gorgeous, absolutely fantastic, opened last year. But then the other plan development as well that I mentioned, so the 50% increase over 2020 numbers. And then we've been adding people, so faculty, staff, students, and more visitors. And, as both Jim and Mark and Abby, have pointed out, we're also looking to continue to reduce our offset purchases. So we're in the final stages of our energy master plan, and many of the details that you heard earlier are, very similar to the things that we're looking at. And I think with each one of our campuses, I was making notes as I was, watching the work at Amherst and Dartmouth, is each campus has its own age and its own peculiarities in its systems. So we do have a central heating plant. We are looking at replacing steam with hot water. And we're at a point when I talked about renewal, all our steam systems are either at or beyond the end of life. So we've begun a process of actually replacing out those steam lines. And the way I got people to buy into the first one was replacing what was on top of the steam lines with an absolutely gorgeous streetscape. So that got a lot of enthusiasm. So we're going to continue on that path. But the building renewals that Abby mentioned are also a significant cost investment. And one of the things that we're looking at is similar to the zones, Mark, that you talked about at Amherst. We're looking at where do you phase, and how do you do it in the most, in a cost-effective way, but also, while making your reductions matter in emissions. So we have several buildings that are already, they'll have hot water systems. So we're starting there. And then after that, we'll move to the ones that really are the big energy hogs on the campus, and then move on to the ones that, there are lots of them, but they really don't, emit that much. So I think, again, the key criteria are not that different. Again, looking at reliability, of our energy sources as well as our systems. We are looking very similar to Amherst at, geothermal wells, and having those under the athletic fields, again, in a way that it's always going to be open space. It's I think, the best way to do it. But also, if you reduce your dependence on gas, you're better set for the long haul. So, we're not stuck, and you don't have a lot of sunk investment in steam if you've renewed using steam, in 10 years' time. So that's that. And then greenhouse gas emissions, and then long-term flexibility. Again, the flexibility is to be able to shift easily between fuel sources and modes. So I think the analysis has been very similar again. And we're aligning with our state's long-term emissions goals. And the other thing that I wanted to use, as a switch to the next slide is going beyond just our heating and cooling systems and energy sources to looking at building performance. So again, pushing the envelope, but also looking at planning and our footprints. Compact development makes a lot of sense. We're looking at a lot more mixed use and compact growth for our new buildings. We've also pushed our LEED, our minimum rating up to gold from silver. And we adopted, the site certification. So that's for sustainable landscape. It's a sustainable landscape, but also just, a better, more comprehensive view of land development. So that's also a standard. And, it's actually been surprisingly fun, because it also gives us an opportunity to educate students. And then energy, I did go over. We do invest $500,000 each year. And this is also in retro commissioning, and then in tracking and monitoring some of our energy hogs, our favorite buildings. And targeting transportation, it is a challenge because of where we are located. So we're in Maine, central Maine. And the way we market the college is you're an hour from the mountains and an hour from the sea, which is absolutely lovely. But you do need wheels to get there. So we're looking at creative ways to make that happen and not require as much driving. So the other thing, that's the other big nut that we are looking at, is our waste. So whether it's composting, landfill waste, construction waste, it's a whole slew of different options. So I'll stop there. Just wanted to thank you all, and hopefully we should have enough time for questions.
We do. Great. Thank you, all of our panelists, for the insights that you provided. Each of you are, like Mina said, dealing with the nuances of your own campus, but really making great impacts and planning out major investments that align with the commitments that your institutions have made. And I think it's really valuable for us in the design community to understand what you're doing on campus, especially for those of us that may work on, say, individual building levels, to see how you think about this as this campus level energy system. I hear a lot of parallels between all of the presenters, one of them being switching to hot water, eliminating the use of fossil fuel to generate heat, thinking systemically about the investments that you might be making in your utilities anyway, and spending that money more wisely to move you in the direction towards your carbon neutrality goals. So I want to invite everyone in the audience to submit questions. Let me start with one to our panelists, and I'll let each of you respond independently. But for those of us in the design community, in the construction community, or for those attendees that are from other colleges and universities, what advice do you have to them for following a similar path, or for finding a way to decarbonize the work that they're doing on their campuses? I'll start with Abby, go ahead.
Oh, well, that's a big one. I think the message, as I think you've been hearing, is that the answer is really probably different for each campus. And you really need to look fundamentally at how are you using energy on your campus, and where the carbon emissions are, how energy intensive are your facilities. And I would recommend start with the biggest problems. You know, like, as I said, our biggest opportunity is the carbon emissions associated with our heating plant, and to eliminate or reduce that gets us really far along in meeting our carbon reduction goals.
Thanks. What about at Amherst, Jim or Mark?
Well, touch on it. Abby mentioned that low temperature hot water can use heat sources, a range of different heat sources. When we started considering our decarbonized infrastructure, there was some hesitancy to say, well, heat pumps, that technology might evolve and might change. And how do we ensure that, you know, that is going to be something we can rely on for the long term? And I think the point we are able to emphasize in a decarbonized infrastructure with low temperature hot water, that because it can adapt to so many different heat sources and so many heat reclamation initiatives, sewer, for example, reclaiming heat from sewer, it future-proofs the infrastructure. And I think that is really important for institutions to consider, particularly if they're having cold feet, if you will, about that sort of capital investment.
Thanks. And Mina, what are your thoughts?
So I agree with Abby and Jim. And I think, you know, sometimes you have to, you know, you're lucky and you are able to take on the big piece and, you know, deal with the entire elephant. Sometimes you have to, you know, take small steps. And, you know, I would encourage folks, you know, even if you think it's a big hill to climb, just keep walking up. Sometimes you can do a small project, a pilot project, and have a show me. And that can also help because you have something that's there. It's you know, it's working, and it proves, you know, what the point you're trying to make. So we have 2 buildings that are already, that have geothermal systems. So the whole fear of, you know, getting into the ground is somewhat mitigated, and they're doing just fine. So when we mentioned it, it wasn't so much, oh my God, is geothermal gonna work? But I do like Jim's point about the long-term flexibility, which is, again, why we're looking at it. But, you know, the fact that we've had 2 smaller projects that actually didn't cost any more, you know, so sometimes it's a mix of big things and small things, but I think the approach for your institution is going to be the one that, you probably know the best. Just don't give up.
Thanks. And as questions have been coming in from the audience, one thing that the design community certainly is really beginning to take seriously as we design facilities that really reduce their operational reduce their operational energy and operational emissions, is a turn towards looking at the embodied energy, embodied emissions associated with construction, with renovations. Could anyone on the panel speak to any initiatives you might have on your campuses around that? Go ahead, Jim.
I'll say that we're contemplating a new academic building, a modest building, about 20,000 square feet. But one of the things we've come to realize is that conventional building strategies result in such a high embodied carbon footprint that even if we had a high performance building from a thermal perspective and an energy perspective, the payback period is so long from a carbon accounting period. So we as an industry, if you can call higher ed an industry, needs to be aware that we can't conserve our way out of the global climate change. It will take too long. So I think we have to look at it from both perspectives. We have to drive down the energy consumption through some of the strategies we talked today, but we also need to address the embodied carbon. One without the other just will not get us there.
Agreed.
Yeah, and I'll jump in on that one. I will add that it would be fantastic to have professional partners in the design field, who will help us with that, because, there is oh my gosh, if you do something different than the convention, it's going to cost you a ton more. And then everyone says, we don't want to go there. But it would be lovely to have some creative, enthusiastic architects, engineers who are willing to dare.
And I will merge actually two questions and direct them to Abby. We had one question around the importance of building envelope upgrades as part of energy master plans. And I know you spoke to one example in your presentation. There's also an earlier question when you were presenting, if you could speak to the use of solar thermal technology in your plan.
Yeah, so we are trying to incorporate envelope improvements, and we basically are doing them across the board for our major renovation projects. We're adding insulation, we're replacing windows. With projects that are not major renovations, to do that level of invasive work would greatly increase the project budget. We are adding insulation, typically like attic insulation, that has a big impact on building performance without a lot of invasive work in the occupied spaces and without a lot of expense. So it's kind of balanced depending upon the scope and schedule of the project. What was the other one? Solar thermal?
Yeah, how are you using solar thermal on your campus?
Well, we just right now have a couple buildings with solar domestic hot water, but part of the conceptual design for our new heating sources would include a pretty large solar field. That is a conceptual design at this point, so we don't have any particular technologies designed and selected yet for that. I mean, it could be flat plate, or it could be evacuated tube, or concentrating, or I don't know. We don't know yet.
And I will ask one final question. Actually comes from Debbie, and actually use this as a chance to hand off to her to make some final comments about SCUP. So Debbie, would you like to ask your question and also discuss your final points?
Sure, thanks. Patrick, this is for any of the panelists, but as an architect, planner, programmer immersed in working on campuses, I'm interested to know how much have the students helped drive and participate in these initiatives across your campus?
I can say that Dartmouth, I think students have had a significant impact on really pushing along the narrative with among the administrators from the president on down to, you know, our administrative and financial leadership on the importance of carbon reduction on the campus. And we have within our engineering programs actually have had students do pretty extensive studies of the campus that have been very supportive of the direction that I talked about in my presentation. And I think that that has had a significant impact on gaining support from all different levels within the college.
I would say very similar experience at Amherst. Our students have been very strong advocates for the climate action plan. In fact, the weekend before the trustees were to vote to proceed from concept to design, they held a session in which a number of our students related the climate impacts for their communities and use that as a means to describe the moral imperative for the college moving ahead. I believe the trustees would have done it anyways, but knowing it had the imprimatur of our student body really galvanized our trustees. The other thing I'll say is we have used a term that is interesting, and it's beyond carbon neutrality. And you say, well, how can a project like this be beyond carbon neutrality? It is when you look at the force multiplier of our students who maybe are inspired by this or learn from it, who go into their private lives and do projects that are significantly more. They affect public policy. They affect carbon taxes. They affect corporations. So I do think, you know, there is a payback beyond just carbon and financial for the institutions. It can go much broader.
Yeah, we have, you know, I think it's a challenge though when you become carbon neutral. Everyone thinks that you arrived and you don't have to do anything more, and that is something that you have to keep at. So we have a competition with our biggest rival in Maine, Bowdoin. So every year the students have this challenge competition for energy and water, and whoever wins gets to keep the other school's mascot for a year. So we've kept the polar bear for quite a while. So, but that's kind of, you know, it's one of those fun things, you know, it keeps the energy going.
Great bragging rights. On that, Mina, thank you very much. What a great session. Thank you all, Abby, Mina, Jim, and Mark, for sharing this information. So valuable, and I think inspiring for us all, even inside out higher ed, but also outside higher education, to see what you can do with so much real estate. I want to mention a couple of BSA SCUP upcoming sessions. May 25th, 4 to 6, the future of learning, with a couple of college presidents talking about where they see learning going post-pandemic. In June 15th, in collaboration with the BSA Equity, Diversity, and Inclusion Committee, a session on EDI on campus with a focus on student life. We're working to do an outdoor environments in the summer, whether it will be virtual or whether we can find a venue for an outdoor gathering. We're hopeful. The announcement will come out in the next couple months. And then in July 11 to 13, SCUP National Conference will be hybrid style, both virtual and in Philadelphia, for those who want to catch up on continuing trends in higher education. Back to you, Patrick.
Thank you. And the BSA COTE committee also has an event scheduled for next month on May 19th from 6 to 7:30, in which we'll have Paul Lucas, fellow AIA, presenting a presentation about sustainable design excursions from Boston to China and back from his experiences. We're excited about that. And like I mentioned earlier, we are looking for the new co-chairs to take over at the end of Michael's and my term starting in June. Anyone who's interested, I put my email in the chat. So with that, thank you everyone for participating and for learning from this great panel. And especially thank you to Mina, Jim, Abby, and Mark. It was a wonderful and really informative session. I was really excited to bring you together to share this message and to learn from you. You bring great insight, and you're also inspiring for what we can do on other college campuses or what we can do as designers and planners in our next projects. So thank you all. And with that, have a good night, everyone.
Thank you.